Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Tarek O'Dali from Business Review, and I will be your host. It is our pleasure to have VTT with us today, who will be discussing biocomposites, insights, and patent landscape. Today's guest speakers are Antti Ojala, Research Team Leader, and David Sandqvist, Principal Scientist in Biocomposites at VTT. I'd like to welcome you to our webinar platform On24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click Submit. We will allocate around 10 to 15 minutes at the end of the session to address any questions or thoughts that you may have. If you click on the survey widget, there are a few questions in there for you to answer in order to provide feedback. You can do this during or immediately after the webinar. If you click on the green resource list widget, you will find a PDF from our speaker with some information relevant to this webinar. And to all attendees, the webinar slides will be available to download with the on-demand version of the webinar. You'll be emailed instructions on how to access this. Please use the yellow Help widget if you require any assistance, and feel free to move, resize, and maximize any of the windows in front of you to get a better view of the slides. But now, without any further ado, please allow me to welcome David Sandqvist.
Thank you very much, Tarek, and thank you very much everyone in the audience for attending. Today, we would like to talk about biocomposites, and we're going to try to cover the patent landscape for biocomposites, some of the current limitations and challenges, some of the emerging materials and novel architectures, and lastly, waste valorization using biocomposites and some of the circular economy. So firstly, a brief introduction to VTT. VTT is the largest research and development organization in the Nordic countries. We have approximately 2,500 on staff in total, and we span a very large area, so research all the way from energy to food science, enzymatic treatment, to novel biomaterials. And today we are representing the people working on biomaterials and bioproducts at VTT. And in total, we are approximately about 40 people working full-time at VTT on biocomposites. And we have a very large and well-stocked facility. And we have a lot of experience working with tailoring of fibers and biopolymers, working with biomaterial process development and high-performance composites, as well as looking at biopolymers and fiber foams. Currently, there are no good international standards for biocomposites. And this is something that we see needs to be developed for the future. At VTT, we have identified at least 4 generations of different biocomposite materials. The first being the traditional wood and plastic composites, and later natural fiber plastic composites. And the 2 more emerging generations are natural fiber biopolymer composites and also nanofiber biocomposites. And not only is the composition important for biocomposites, it's also the morphology, which is true for traditional composites as well. And these can include short fiber, continuous fibers, or particles and powders. And together with the processing of these materials, these really help to define the performance and the material properties of composites. And now, we would like to talk about the patent landscape for biocomposites. The patent landscape that we will show you today has a focus on lignocellulosic composite applications, both material and processing patents, and we have tried to be inclusive rather than exclusive. And the total number of patents is approximately 14,400, so it's a very big data set. And the covered topics that we've included includes the classic wood composites, such as plywood and wood particle board, wood plastic composites, agricultural fiber composites, and wood fiber composites, as well as nanocellulose and all cellulose composites applications. And we have deliberately excluded bioceramic composites or biomedical composites from this patent landscape, even though that they are biocomposites. And in the patent activity from approximately 2000 forward, we can see the same trend as we see in quite a number of areas. So it's a growing trend and interest in biocomposites, and in particular in the last couple of years. And just to highlight the data for 2014 and 2015, they only include the publicly available patents. So these are not the final numbers for these years. And looking at patent countries, we see a clear trend where China is leading in the number of patents. And we have seen a similar trend for quite a number of the different research areas for VTT. And the trend is actually really astounding for biocomposites. And China's current patents in the last 5 years now exceed the total number of patents in biocomposites in both the United States, Japan, and the EU. Secondly, we can actually start to see a drop of patent activities in the United States in the last couple of years, as well as in Japan and in the EU, whereas there is significant growth, continued significant growth in China. For the application area, because we have included the traditional wood composites, boards and sheet materials dominate the application areas, as well as construction materials. But after these classical applications, we're looking at plastic foamed materials being a significant application area, as well as molded plastics and automotive parts. And these include a lot of materials from the third and fourth generation of biocomposites. And there's a lot of detail on this graph, and you'll be able to go through the detail later on in the PDF. But just a few things that we want to highlight. So even though China is still very much dominating the total number of patents, some of the classical organizations still have the largest amount of patents in the area, such as BASF, Panasonic. But both of these organizations have really dropped off in the number of patents in the last 5 years. And we can instead see a growing demand in companies looking at novel application, novel biocomposites and novel application areas, such as, for instance, UPM and Stora Enso that we have highlighted here, which have had a significant growth, almost starting from nothing in the last 5 years. Now, we would like to talk about some of the current limitations and challenges with biocomposites. First of all, we have this slide where we want to show the amount of cellulose content in the different application areas. And to the right in this graph, we see some of the classical wood application areas, such as pulp and paper, non-woven and classical wood composites, which have a large amount of wood or cellulose contents. In the middle of the graph, we see some of the more developed biocomposite, new biocomposite areas, such as injection molded and 3D printed materials. And to the left of the graph, we see the new emerging materials, such as nanocellulose composites, which only require a very small amount of cellulose contents. And conversely, we also wanted to show the value versus volume proposition for these materials. So the classical wood products, such as pulp and paper and wood composites, have a high volume but a relatively low value, whereas the new emerging biocomposite materials have a much higher value but at a smaller volume. And the drivers for biocomposites is very much the same as the drivers for circular economy. And it's to create, rather to reduce the amount of virgin material use, to recycle material whenever possible, and to renew or to reutilize material as effectively as possible. And the targets are to create light, high-performance materials and to replace oil-based materials as much as possible and maintain production efficiency and material efficiency in the process while maintaining safe materials which are visually appealing. And in this Ashby plot, we just want to highlight that nature has been very effective in creating high-performance fibers that can easily compete with man-made materials. And in the top right-hand part of the graph, we see some examples of this, such as cellulose, flax, hemp, jute, and silk. And these materials perform very well in terms of tensile strength in Young's modulus. But they can also be quite delicate on their own. And to utilize them in an effective manner, they need to be incorporated into a composite kind of material. And if we take cellulose as an example, it has very high stiffness and strength in its native state. But when incorporated into a composite material such as wood or wood-like material, then we lose quite a large amount of those strength and stiffness. And if you look at the green area, which shows wood and wood-like materials in the center, this is sort of the best case scenario, even for natural materials. And this is the same challenge that we face with biocomposite materials as well. And in this Ashby plot, we're showing all kinds of materials, including man-made. And here you can see biocomposites situated in blue, approximately in the center. So it's a mix between the polymer properties and the wood or wood-like properties. And essentially, the biocomposite is one order of magnitude lower in mechanical performance compared with glass and carbon fiber composites. And the two main challenges with biopolymer composites is dispersion and compatibility. Most natural fibers tend to be hydrophilic, whereas most of the matrices are hydrophobic. And for this reason, a compatibilizer almost always required to get the best performance. And for the same reasons, achieving effective dispersion is equally challenging. And we often need to employ a good method to disperse the fiber inside of the matrix. Not only are the material properties important, equally important is the process by which we're processing the material. And existing processes are predominantly developed for conventional plastic and composite. And they tend to be too harsh for biocomposite materials. And effectively optimizing the processing of these materials can often yield as much as the same as the optimized material performance. And this often requires new ways of thinking about the processing, as well as about looking at new designs of the biocomposite product. And now, I would like to hand over to my colleague, Antti Oila, to talk about emerging materials.
So, thanks, David, and hello to all of you from my behalf as well. So, next I'm talk about emerging materials and novel architectures. So, here is shown how we see the biocomposites today. So, the biocomposites are something that give added benefits to synthetic plastics or biopolymers. The biocomposites, they can be fully bio-based or partially made of bio-based material. Biocomposites as plastics, they can be fully biodegradable or they can be also durable materials. In biocomposites, one can also valorize different kind of size stream and waste material streams. The biocomposites have a lot of synergies with conventional plastics. They can be used in many cases in the same application or similar application as conventional plastics. The logistics are very much the same, and they can be also recycled and or used for energy recovery in the same way as the conventional plastics are used today. The additional benefits of biocomposites are the improved performance to conventional plastics, but they also can be used to reduce the environmental impact or improve the material and energy reutilization. The essential part of biocomposites are the natural fibers. And often one has to modify or mechanically treat the natural fibers before they can be utilized in the biocomposites or to improve the performance of the fibers in biocomposites. So at VTT, we have been working with different methods to modify the fibers and to process the fibers. These methods can be classified as physical, chemical, or enzymatic. For example, as an example of chemical methods, we have been used epoxidation, esterification, and esterification to improve the compatibility between the polymers and the fibers. Currently, the main method what we use to modify fibers and to improve the processability of natural fibers in production of composite materials is our VTT compactor process. It's so-called mechanochemical process where we are able to compact the fibers so that they are easy to feed into extruder, as well as we can also chemically modify the fiber. So it's in a simple process where the fibers and the chemicals are mixed together, after which they are compacted to compact pellets in a VTT compactor, for which we hold a patent. And after compacting, these pellets can be fed into extruder. So as conclusion, the benefits of this process are that first, you get pellets that are very easy to feed into the extrusion process. You can very cost efficiently combine chemicals with the fibers. And also you can work at very high consistency, which further improves the economics of the method. So next I'm going to talk about three different research examples where this process has been utilized. So first, we have a chemoenzymatic method. So in this process, we improve the compatibility of the fibers with the plastic materials by using chemoenzymatic treatment, and this chemoenzymatic treatment was then carried out in this VTT compactor. So we had CTMP fibers that were first enzymatically activated and then chemically modified. And in the picture on the left-hand side, you see the impact of the chemical modification on the mechanical performance of the fibers. So you see, compared to mid-PLA and the PLA CTMP composites without chemical modification, you see clear improvement after the chemical modification of the fibers, both in tensile strength and modules. Additionally, the impact strength was improved. As a consequence of the improved compatibility, the dispersion of the fibers in the PLA and PHP matrices was significantly improved, as can be seen in the picture on the right hand side. In the second example, we again utilize this VTT compactor and the mechanochemical modification method to improve the performance of our natural fiber reinforced PLA composites. In this case, we tried a different type of chemical additives with two different kind of cellulose fibers. And as you can see in the graphs shown on the slides, we were able to significantly improve the performance of the cellulose fiber reinforced PLA composite. In the best case, we were able to improve the impact strength of PLA by 60%, which is quite a significant improvement considering that the major weakness of PLA material is typically the low impact strength. The last example highlights the importance of the compatibility. So, in this example, we used a nanocellulose mixed with polyvinyl alcohol. So, polyvinyl alcohol is highly hydrophilic, as is a nanocellulose. However, the compatibility is still far from optimum. So, in this case, we modified nanocellulose with an epoxide group so that we could able to form a covalent cross-linking with the PAVA matrix. In the figure on the left-hand side, you see the evolution of the tensile strength as a function of the nanocellulose content. As you see, when we had 1% of nanocellulose without any modification, there is hardly any improvement in tensile strength. However, the same content, so only 1% of nanocellulose, after the chemical modification and after the material is able to form a covalent cross-linking with PVA, we have improvement in strength. We have over 300% improvement in tensile strength. The similar major improvement is also seen in modules. In this case, the modules of the modified nanocellulose composite was over 2 times higher compared to unmodified. Furthermore, the strain at break was also slightly improved after the chemical modification, which means that the overductility of the material was significantly improved compared to unmodified composite material. As a final example, I have a commercial case, a research case we did together with Puusteli Group. Puusteli is a Finnish-based company producing kitchens. So Puusteli wanted to reduce the environmental burden of their kitchens. So in this project, we developed together with Boostel biocomposite materials that then could replace existing chipboard and particle boards in their kitchens. The project was successful, and there's now a new kitchen concept available from Boostel where biocomposites are used. The benefits of the new kitchen concept are that it's much lighter than the old kitchens. It has significantly reduced raw material consumption, and the overall carbon footprint is over 50% lower than in the old kitchens. So next, I'm going to talk about something about emerging polymeric materials. So, as you know, not only the biofibers are important for biocomposites, but equally important are the biopolymers. Here we have a commercial case with Cargill we did some time ago. So Cargill needed a new process, a new material that could more efficiently convert sugars to lactic acid. In this project, VTT developed a new yeast strain that could convert bio-based material more efficiently to lactic acid. And as you know, the sister company of Cargill Naturwork is today the largest PLA producer in the world. So, the next example is about PGA. So VTT has been developing a new PGA process. We call it VTT PGA. As you know, this PGA material has superior oxygen barrier properties, and it also has excellent mechanical performance. The material is targeted for barrier application in film and food applications, and it has a high potential, or these markets have a very high potential. The barrier markets are over 1 billion in size. So VTT has already demonstrated this PGA production in hundreds of kilos size scale. The material has very high molecular weight, 250,000 grams per mole. We have applied it for multi-layer films and tested in several different applications. Here we compare this VTT PGA with existing commercial PGA and also with some existing high-performing oxygen barrier material that are commonly used in packaging applications. So the major limitation of industrial PGA, commercial PGA, is that the production costs are very high. So this VTT, this patented VTT process can significantly reduce the production costs of PGA and simultaneously maintain the excellent oxygen barrier properties and mechanical strength properties that PGA has. So overall, this VTT PGA is very much comparable or even better than the materials, the existing materials that are nowadays used in application where high oxygen barrier properties are needed. So, lastly, I would like to talk about lightweight architectures. So we see at VTT that foaming of biocomposite is something that is becoming very popular in near future. By foaming, and especially by polymer foaming of biocomposites, you can overcome some of the shortcomings that biocomposites have. Firstly, you can significantly reduce the weight of biocomposites. And at the same time, one can improve absolute impact strength and ductility of biocomposites if you are able to control the cell formation and the cell size. Furthermore, by foaming, the specific stiffness and the creep properties of biocomposites can be significantly improved. VTT has been very active in polymer and biocomposite foaming research in the recent years. We have invested in facilities where we can do laboratory scale foaming starting from 2 kilograms and go to pilot scale extrusion foaming and use 100 or over 100 kilos of material in a day. The extrusion foaming of biocomposites is much more challenging than just foaming of conventional neat plastics. Here is one example shown how we have been able to improve the processability of biocomposite materials in extrusion foaming process. So in this example, we had PE material filled with 30% thermomechanical pulp. The foaming agent what he had here was CO2 and we used extrusion foaming process. With the reference material, so with TMP reinforced PE, we had difficulties to maintain the process stability. So the process was very unstable. We ended up having very large cell size, and also the distribution of cells was inhomogeneous in the material. However, when we used a certain polymeric additive in the process, the foaming process became stable, the cell size was significantly reduced, and also the foaming degree was improved. In addition to polymer foaming, VTT has been working actively and studying actively foam forming. Foam forming is typically used in board and paper industry, but the same technique can be also applied for making novel biocomposite materials. The good benefits of foam forming are that it's a very efficient method to mix and to disperse together very heterogeneous materials. One can use their long or short fibers, particles, and powders of different size, and still have a very homogeneous mixture. In our view or vision, we see that foam forming can be used to make thermoformable sheets in a continuous process, and also we can also use the process to make premixtures, homogeneous premixtures of materials in a very gentle way, without breaking the fibers, and use these premixtures in extrusion and injection molding processes. Here are some examples how we then have utilized the foam forming to make composite materials. We have made thick layered structures that can be used to replace EPS type of materials in packaging applications. We have used foam forming to make insulation, acoustic and thermal insulation panels with excellent performance properties. We have also made thermoformable panels and laminates. We can easily see that this method is also very suitable for making sandwich structures with different materials in the skin and the core layers. So, next, I will hand over back to David.
Thank you very much, Antti. And now, lastly, we would like to talk about some of the forest and agricultural side streams, and essentially waste valorization. And waste valorization is material side streams, so biocomposites and composites made from waste streams is an area where biocomposites really come into their own. And the example that you see below is the pulp and paper industry, but this is applicable to many different industries and to many different materials. And the benefit of making biocomposite materials from waste streams is that we're able to create a product with valorize a material that previously only was a cost, as well as creating new materials with added benefit. And biocomposites are a really good application area for many of these waste and side streams. And side streams and waste streams have been demonstrated in composites for a long time, at least over the last 2 centuries. And some of the examples that we have here are from pulp and paper side streams, and they can include de-inked pulp, sludge, or coarse fibers, as well as fly ash. And here we see some of the data from composites prepared from these different materials. And we see the reference material to the right, which is highlighted in red, and they're made from traditional wood flour and kraft fiber. And if we look to the left-hand side of the graph, we can see quite a number of different waste and sludge materials. And these compete really effectively with the reference wood fiber materials. And in particular, we want to highlight that the de-inked pulp and the coarse fiber sludge have approximately this very similar tensile strength as the fiber references. And the fly ash has even higher impact strength than the wood flour and kraft fiber composites. And the conclusions that we would like to end with is that we see that for biocomposites, material compatibility is really key for performance. And equally important is optimizing the process for the biocomposite material at hand. And this can be different for the different materials. And in particular, we see that thermoplastic biocomposites have a huge opportunity for the circular economy and for recycling. And this can include quite a number of application areas. And lastly, foaming of biocomposite materials gives us the ability to improve the performance even further, utilizing less energy and less raw material. And with that, we would like to end and hand back over to Tarek.
Thank you very much. So at this point, it's time for today's first poll question. So you should see a question in front of you with some possible options. And the question is, which area of biocomposites are most interesting to you? And audience members, if you could please select the answer that's most relevant for you and click submit. So the options are material development, process development, and applications. So I'm just going to ask the speakers, what do you expect to see from this poll?
So, good question. So applications are of course very important, but at least to my opinion, the applications are already there. So it's more about material development and process development that we can reach the existing application and have new applications. So I am definitely would vote for the material development or the process development.
All right, lovely. So let's actually, I think that's enough time for the audience to have voted. So now let's see what they actually did say. And oh, there you go. So the winner is material development with applications not too far behind. Does that result surprise you?
No, actually, something I expect.
Lovely. Okay, so we've got another poll question straight away. So audience members, the same thing again. And this question is, what is your main motivation to incorporate biocomposites in your business? And the options are cost reduction, material savings, environmental benefits, improved properties, and branding, green label. And if you could select the answer that's most relevant for you. Sorry, if you could select the answer that's most relevant for you and then click submit. And then we'll see what happens. So speakers, let's hear from you. What do you think we're going to see?
So there's several good options. It's really like cost reduction is in many cases. I think that's a major benefit, especially when you are utilizing recycled materials. But also improve properties. You can really improve the properties of polymer materials by using novel processing and material modification methods.
All right, let's see what they actually went for now. So okay, it's quite an even split. We've got the winners are improved properties and environmental benefits, and cost reduction is almost on the same level as those ones. So is that what you expected to see?
Maybe even a bit surprised of the environmental benefits.
Yeah, positively surprised.
Exactly.
Right, that's good to hear. And we've got one last poll question for you, audience members. So if you'd like to go ahead and vote on this one as well. So we've got, what is the main bottleneck on your way to commercial biocomposite applications? And you've got some choices here: availability, performance, cost, technology readiness, market pull readiness, or knowledge and know-how. And if you could please select the answer that's most relevant to you and click submit. And while you're doing that, speakers, what do you think the result will be for this one?
Now, in our experience, and also been confirmed externally, knowledge and know-how tends to be the biggest bottleneck. And secondly, it's technological readiness as well as the performance of the material.
Okay, lovely. So I think that's given the audience enough time to vote, and let's see what they voted for. Oh wow, okay, so it's all over the place a little bit, but we've got technology readiness as the winner there, and that's along the lines of what you guys said, right?
It is, and it is a little surprising that it's so high, but I think that's coupled with know-how in terms of what is actually possible already. Yep. Thank you very much, Tarek. And if you would like to get a chance to meet us in person, the next opportunity will be already next week at the International Wood Biorefinery Week in Stockholm, where both I and a number of my colleagues will be present. And please stop by if you have any questions about either biocomposites or material development. Please stop by our booth, and we will also have some showcases at the fair. And also, we've had quite a number of requests here in the past about samples of the different kinds of biomaterials and biocomposites. And for this reason, we have now developed a biocomposite sample folder, which is available for sale. And this includes different composite samples using different polymers and different fibers, as well as different colors that can be achieved with these materials. And should you be interested, then you'll see the contact details later here in the slides. And please get in contact with us should you be interested in purchasing one. And with that, we would like to hand back to Tarek for questions.
Thank you very much. So just a reminder for the audience, we're about to go into our questions and answers session. So in order to ask your questions, you can send them in via the questions widget. So just type them into that box at the top left-hand corner of your screen, and then click submit. And I'll begin with a question here. We've got one here. I lost the sound for a while in the beginning. What was your main message or conclusions regarding the current patent situation?
The main conclusions are, we looked at a broad scope of the different patents, but the main conclusions are that biocomposites is growing very, very actively. Some of the old areas of composites are tailoring off, whereas others are gaining significantly currently. And China overall is definitely leading the field in terms of patents, whereas the more traditional areas such as Europe and United States are looking more at the very latest generations of biocomposites.
Okay, thank you for that quick recap. And now the next question is, what are the barriers for a successful market penetration of biocomposites?
I would say that there are several different barriers or obstacles. One is the awareness that how aware people are of the possibilities and properties of biocomposites and where they could be utilized. But also there is, in some cases, there's also still in performance. They are lacking in performance in certain applications. So it's both the awareness and the performance that has to be improved.
Thank you for that. Okay, so I've got another question here, and that is, I have not heard any comments on two of the most common problems with biocomposites, and that's odor and impact strength. Could you comment, please?
They are true, and there's also a third one, which is also creep resistance. And odor and impact strength are not really an issue any longer, but it requires very specific processing conditions and pretreatment of the fibers, as well as selecting the right polymers for the application. So it depends very much on the application and the choice of the fiber and the polymer system in use, as well as the processing. But it's now possible to make biocomposites that equally surpass the conventional composites in terms of impact strength. It's challenging but doable, but odor is not really an issue any longer. It needs to be considered, but not an issue. Creep performance is still a challenge as well.
Okay, thank you very much for the answer there. And the following question is, your presentation was very focused on PLA and PGA. Are there any other materials that you see in the future of biocomposites? So here were some selected examples, with just a few examples we have been working with. Of course, we have been working with very many different polymer materials. So PLA is interesting materials and will have a role in biocomposites, but definitely conventional plastics like PP, PE, they will be used in composites, and they will definitely have a big role in biocomposite materials in future. Okay, thanks for that insight. And another question now is, which is the functionality or material property that is most sought for when selecting a biocomposite?
This depends very much on the application area. And you can have application areas where you're looking for durability, and in other cases you can have applications where you're looking for biodegradability, for instance. You have the whole span, and it depends very much on the application area. And there's a broad span in the different biocomposite materials as well. So for some application areas, it's definitely the cost, which is the dominating factor. In others, it's the material performance. And in some cases, which are less common, it's the environmental footprint and also biodegradability. So it depends very much on the application area.
Okay, thanks. That answered that question perfectly. And we've got another one for you now. What is the maximum amount of cellulose fiber that can be added to the PLA biocomposite?
So that depends of the processing method. So if we are aiming for injection moldable materials, it is 50 weight % is close to the maximum. There you cannot go much further than 50. But 50 we have been using in our labs. In extrusion processes, again now it's discussion whether we have fibers or wood flour, for example. So with particles, one can go somewhere between 70 and 80. With fibers like pulp fibers, you are probably a bit lower than 70.
And foam forming?
And foam forming, okay, there is no limitation. Of course, then they come how much resin the performance. So there you can have very high fiber content, but of course at some point the content, the resin, you need the resin to have some to get the resin to bind the fibers together. So maybe you are around 90 with foam forming,
or even higher,
or maybe even higher.
Right, okay, thank you for that. So the next question now is, what are the different business models of VTT, and do you license your technology? So
VTT does direct customer work. So we don't sell any products. So we do customer research for companies. We do joint research with companies and direct customer research with companies. So we like to have direct research projects with companies, but we don't make any materials for sale.
We do license our technology.
Yeah, exactly. Yeah. So we like to develop the materials or processes to point where they can be then industrialized. That's the step where we are. So we can do piloting, but not go to industrial processing. At that point, we will hand out or give out the patents and license the processes.
Amazing, thank you. And another question here is, how does VTT overcome compatibility issues between fiber and polymer?
So, as we showed in the presentation, VTT has trialed quite a number of different techniques in the past, and these include both the physical pretreatments, chemical pretreatments, as well as enzymatic and combinations thereof. And currently, we favor a mechanochemical treatment, so where we include a chemical component together with a compacting process, creating pellets which are then easily fed into an extrusion process. And this is predominantly for short wood fiber materials. For longer fiber materials, such as agricultural fibers, other techniques will be more applicable, for instance, in terms of weaves and things like this. Often they will have a preliminary wash or a chemical treatment prior to being compression molded, for instance.
Okay, thank you very much. Next question now. Does VTT have any commercial scale biocomposite processes?
Shortly, no. So we have pilot scale equipment for extrusion and for foaming. So with pilot scale, we mean that we can process hundreds of kilos in hour, but I would say that no, we don't have any like industrial production scale machines for production of biocomposite materials.
Okay. But we have another question here. Does VTT have any pilot scale machine for polymer or biocomposite foam?
So there we have a tandem extruder where we can, it's close to piloting scale, so there we can process like 30 kilos per hour. So it's quite close to, it's relevant for piloting of extrusion foaming process.
Okay. Now the next question is, how would you rate biofiber composites against conventional GF or CF composites? How much promise would you say biocomposites hold in structural applications?
So, for comparing biocomposites and glass fiber, biocomposites today, the very best that we can achieve, compares very, very favorably in almost all aspects except for creep. And to overcome the challenge with creep, we would need to incorporate, one solution could be to incorporate long fibers together with short fibers in the composites. But we compare very, very favorably in terms of recycling, in terms of environmental footprint, and waste disposal of the final material. And glass fiber composites tend to be very heavy, high density, whereas biocomposites is only about approximately half or 2/3 of the density of glass fiber. Carbon fiber is still, in terms of absolute performance, will outperform biocomposites, but I would like also to remind that it is possible to make carbon fiber from natural resources, such as lignin, for instance, effectively creating a biocarbon fiber composite material.
It's also good to remember that in many cases, although if natural fiber composites are a bit lacking in performance compared to glass fiber, in many cases that performance level is already good enough. So you don't necessarily need the maximum performance.
Okay, thank you. I think we have time for just maybe one or two more questions. So here's one. Do you think there is still room for improvement in the mechanical properties of commercially available cellulose reinforced PP by better compatibility between fibers and matrix?
Yes, I think so. So there's room for improvement in the chemical compatibility, and there's also room for improvement on the processing side to achieve better dispersion and maintaining the aspect ratio on the fibers more efficiently in the process.
I also see that by chemical modification of fibers, one can improve this, how the fibers will survive and maintain the dimensions in the processing. So definitely there is room for improvement.
All right, thank you. And this is going to be the last question, and I think I can answer this one. Where can I download today's presentation? I can tell you that to all attendees, the slides will be available to download on the on-demand version of this webinar, and you're going to be emailed instructions on how to access this. So you'll be able to get access to those slides very soon after the webinar. So that just leaves me to thank Antti and David for what was a great presentation, and of course to thank VTT for sponsoring this session. And to all the attendees, as I said, you're going to receive an email very shortly, and I will tell you how you can access the on-demand version of the webinar, or you can access this directly through our website, and that website for you is www.business-review-webinars.com. And once this webinar ends, today's survey will appear in its place, and we would very much appreciate it if you could answer the questions in there for feedback. I will also say that the resource list contains a PDF file you can download, which has more information relevant to this webinar. And we look forward to sharing further webinars with you, so please do keep an eye out on the website I just mentioned, and feel free to follow us on Twitter, that's @BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. To the speakers, is there anything you'd like to say to the audience before we end the webinar?
I think we just want to thank you, all of you, and wish you have a nice day or evening.
Yes, very much, and we look forward to hearing from you in the future.
Yeah, we'll be forwarding on the questions from everyone who didn't get a chance to have theirs answered, so you can expect a response hopefully from the speakers or from VTT. And with that said, I will just say thank you once again for attending, everybody, and I hope you all have a lovely day.